Welcome all. We shall see the next problem on material balance. It's example 3. Overall analysis for a continuous distillation column. So this is the problem. What is given in the problem? A binary mixture consists of 35% benzene and 65% toluene are continuously fed to the distillation column at a rate of 1000 kg per hour. So what is given? 1000 kg per hour mixture, feed mixture, that is comprising of benzene and toluene is fed to the distillation column. Okay, distillation column, and its composition is actually 35% benzene and 65% toluene. That is 35% benzene and 65% toluene is the composition of this binary mixture. Okay, binary mixture. Then whereas the distillate flow rate was 10% from the feed flow rate. Okay, so what is again given? 10% is the distillate flow rate, that is the upstream. Okay, that is the upstream is 10% of the total feed that enters into the column. Okay, so distillate flow rate is 10%. Okay, 10% of the total feed flow rate that enters the distillation column. Again, the distillate top product, that is the top stream, contains 85% benzene. Then what is asked to determine? Quantity, total quantity, composition of the waste stream. Okay, composition of the waste stream. So this much is the data given, and we've been asked to find out the composition of the waste stream. Okay, total quantity as well as the composition of the waste stream. So first of all, we have to draw the flow chart. So this is a flow chart. Okay, so here this is a distillation column. The feed material is indicated by F, that is the notation that we have taken for a feed material as F, which is 1000 kg per hour that enters into the distillation column. So this feed material consists of 35% benzene and 65% toluene, which is given in the data. Okay, so whenever we are performing a distillation, it means that there is a upstream as well as a downstream. Okay, downstream is the content that remain in a distillation column. Okay, so the upstream, that is the upstream would consist of is actually given in the data, is given in the problem that it is 10%. Okay, the flow rate of the distillate or the flow rate of the upstream is 10%. Okay, 10%. Okay, 10% to the feed rate that is entering into the distillation column. Okay, moreover, what is given? The distillate, okay, the top product, that it contains 85% benzene. Okay, 85% benzene. So this is a distillation column which gives the saturated vapors. Depending upon the boiling point, the saturated vapors are created. These saturated vapors then go into the what we say condenser, where it condenses, and the phases are separated. Okay, the phases are separated, and out of that these phases may be collected, or may be separated as or it may be separated as a part as a distillate, and part can be sent back to the distillation column as a reflux. So this is actually happening in the distillation. So we all know that the part of the condensate or the part of the condensate is sent as a reflux to the distillation column, and part of it is collected as a distillate. Okay, so that distillate content 85% of the benzene. Okay, that distillate content 85% of the benzene, and this distillate is 10% to that of the feed that enters into the distillation column. Okay, 10% of the feed that enters into the distillation column. So 85% one of the content, that is benzene, is given, so remaining would be the toluene. Okay, toluene 15% would be the toluene. So distillate is p kg per hour, suppose. Okay, p kg per hour, 10%, that is this p is 10% of the total value of the feed that enters into the distillation column. Okay, so what is been asked to us? Bottom stream. Okay, the amount or the quantity of the bottom stream. So we would take here one unknown, that is W, and this W would carry benzene as well as toluene, that is this is composed of benzene and toluene. So the mass fraction of benzene we want to find, as well as the mass fraction of the toluene, or the amount of benzene in the waste, amount of toluene in the bottom stream. I must say it's not a waste, because through that again we can perform the distillation, and remaining amount of benzene again can be separated by the distillation process itself. Okay, so this is a bottom stream, and in this bottom stream there is a percentage mass fraction or mass percent of benzene is there, some amount of benzene is there, toluene is also there. This is also unknown. Moreover, the total quantity, okay, total quantity in the total quantity of the bottom stream also is unknown. So this is what has been asked in the problem. Find out the calculate the quantity and composition of the waste stream. Okay, so this is the composition, that is benzene and toluene together make this bottom stream. Okay, and the total quantity of the bottom stream is also need to be identified. Okay, so how much it is bottom stream. So this is a data. This is the data that we have put on a flow sheet. Okay, put on a flow sheet. Now we will go for the calculations. So for calculations, what we do, we take the basis of calculation as 1 hour. Okay, basis of calculation as 1 hour. Here it is given that this is moving, or this is entering into the distillation column per hour. Okay, so basis of calculation we are taking here is 1 hour. We know that the feed material enters is 1000 kg, but we don't know. Okay, we don't know the P, that is we have assumed this as P as a variable which is 10%. Okay, which is 10% of the total feed that enters the distillation column. This P is 10% of the feed that enters the distillation column. Okay, so this P is to be calculated. Moreover, the bottom stream W and the composition that in terms of mole fraction or mass fraction, or in terms of mass percent, this composition can be found out. Okay, can be found out. So first of all we will find out this P. Okay, this P, that is the total amount present in the distillate. Okay, total amount of distillate that is leaving the distillation column in the form of vapors. Okay, so here the basis of calculation is 1 hour, the feed enters is 1000 kg. Then we will make the calculation for P. Okay, for P, how this P can be calculated? We have one formula. What is that formula? Weight percent is equal to mass of a solid divided by mass of the solution multiplied by 100. Okay, so we know that weight percent is given, that is 10% of the feed, 10% of the distillate. Okay, or the flow rate of the distillate or the upstream is 10% to that of the feed that enters the distillation column. Okay, 10%. So weight percent of the distillate that is flowing upstream. Okay, flowing upstream is given. Okay, so 10% is given. So mass of the solute, that is P, is need to be identified. Okay, the mass of the solute, actual how much is the amount of this P is to be calculated, and the mass of the solution, that is the mass of the solution is this much feed material. Okay, this much feed material that enters the distillation column, out of which 10%, okay, 10% vapors goes upstream. Okay, goes upstream in the form of saturated vapors. Okay, so mass of the solution is 1000 kg multiplied by 100, because this is a weight percent calculation. Okay, this is the weight percent calculation, and therefore it need to be multiplied by 100. So put these values in the equation. So weight percent it is given 10, that is 10%, which is equals to P, that is P we want to find it out, divided by 100 divided by 1000, sorry, divided by mass of the solution is 1000 multiplied by 100. Okay, multiplied by 100. This P value comes out to be 100 kg. Okay, this P value comes out to be 100 kg. So this is the simplest way to calculate the weight percent of any material. Okay, so we have used this simplest formula and calculated the weight percent of distillate that is flowing as a saturated vapor through the distillation column. Okay, through the distillation column. So P is identified, it comes out to be 100 kg. So here P is identified. Now what shall we do? We will do the material balance. Okay, material balance, there is a chance for us that we can do the material balance on entire process, or individually each of the unit can be taken into calculation and can find out the unknowns. But here for our convenience we would calculate the entire material balance, because F we know, okay, F we know, P just we have calculated, and W we don't know. So it is possible that W can be calculated, because this is the overall material balance. Okay, feed enters F, that is feed enters, and some distillate is vaporized. Okay, upstream is there, the quantity of upstream we have identified, and what is in the downstream. Okay, what is in the downstream, that is W, that we can find it out. So this is a overall material balance, I must say. This is a overall material balance. So overall material balance can be done over here, because this would be very convenient for us to calculate the overall material balance. Okay, so overall material balance, that is input is equal to output, because this is a steady state process. So you can take the overall material balance as left hand side F. Okay, input as a F and output is P plus W. Okay, P plus W. Put the values of all the variables. We would get the unknown variable W as 900 kg. Okay, 900 kg. So the bottom stream contains 900 kg of what we say binary mixture, in which benzene percent as well as toluene percent may be there. That is, this bottom stream consists of this composition. So here by overall material balance we could be able to calculate or found out W, that is the bottom stream. Now we will perform material balance on each of the individual constituent that make the mixture. Okay, that make the mixture. Okay, so first of all we will do the benzene material balance. Okay, benzene material balance. So when we perform the benzene material balance, we have to consider both input as well as output. So what is coming, how much is the benzene present in the total quantity that enters into the distillation column. Okay, so this is that quantity. Okay, in terms of mole fraction, or in terms of mass fraction, I must say. In terms of mass fraction, this comes out to be 0.35, or in terms of mass percentage is 35%. Okay, it is 35%. In terms of mass fraction, it is 0.35. So multiplied by 1000. So what we get is the amount of benzene present in the total quantity. Okay, total quantity, that is in 1000 how much is the quantity of benzene present. So we use the simple formula as mass fraction is equal to mass of a substance divided by the total amount of a substance. Okay, total amount of a substance. So the total amount is 1000 kg, which is actually benzene as well as toluene. So this is a total amount. So it is in the denominator, and in the numerator it would be a mass of that substance, and what is given here is the percentage. So in terms of percent you can calculate, or in terms of mass fraction you can calculate. 35% can be converted into mass fraction. Okay, so here for our convenience this percent is converted into fraction, mass fraction. Okay, so mass fraction multiplied by total quantity, what it gives is the amount of that particular solute, or the amount of that particular constituent present in the total quantity. Okay, present in the total quantity. So this is a left hand side. So just do it in the right hand side. or towards the output side. So output side is as we are making a benzene material balance, so benzene in the upstream is 0.85 sorry 85%, and its mass fraction is 0.85, which is multiplied by 100. That is p value we have calculated. It comes out to be comes out to be 100. So 0.85 multiplied by 100, that means that the amount of benzene present in 100 kg of distillate. Okay, amount of benzene present in 100 kg of distillate, plus what is there in the bottom stream. Bottom stream W we have calculated. So W multiplied by percentage of benzene, or the mass fraction of benzene in W. Okay, mass fraction of benzene in W. So kg of benzene in W, or W is equals to W is what we want to identify. So here it comes out to be, okay, it comes out to be kg of benzene in W, that is 265 kg. Okay, 265 kg, 265 kg. Similarly, we can do the metal balance calculation on toluene. Okay, metal balance calculation on toluene. This is a metal balance calculation on benzene. Okay, benzene. So benzene calculation we have performed, and it comes out to be 265 kg. Okay, 265 kg of benzene. Okay, 265 kg of benzene is present in the waste. Okay, 265 kg of benzene is present in the waste. Okay, so W we know, multiplied by, suppose we take one variable as benzene in terms of mass fraction in the bottom stream. So that we have calculated over here. Okay, we have calculated over here, or we can take W as directly. Okay, bottom stream as directly. So in the bottom stream, how much is the concentration, how much is the quantity, that is the unknown thing, can easily be calculated. So here W we know, multiplied by, suppose, the mass fraction of benzene. Okay, mass fraction of benzene. So what we would get is the kg of benzene present in the bottom stream. Okay, kg of benzene present in the bottom stream, it comes out to be 265. Similarly, we can make the metal balance calculation on toluene. So here toluene metal balance, to the left hand side. So toluene, the amount of toluene present in 1000 kg of the feed material, this is 0.65 into 1000. So amount of benzene present in amount of toluene present in 1000 kg of feed material, which is equals to amount of toluene present in distillate. Okay, amount of toluene present in distillate. So this is the mass fraction multiplied by total quantity. It gives the amount of benzene in distillate plus kg of toluene in waste, kg of toluene in downstream. Okay, so this comes out to be 635. Okay, 635 kg. Okay, 635 kg. So here we have found out the total material balance as well as balances or metal balance on each individual constituent that forms the feed mixture. Okay, that forms the feed mixture. So here the total mass balance, okay, total mass balance, we can find it out. W kg of benzene plus kg of toluene. So this comes out to be 900 kg. Okay, 900 kg. Okay, here it comes out to be 900 kg. Kg of benzene and kg of toluene. So this comes out to be 900 kg. Okay, so left hand side balances right hand side. Now what we want to find out, the mass fraction of benzene in waste. Okay, mass fraction of benzene in waste. Okay, mass fraction of benzene in waste. So what is the mass fraction of this benzene? So mass fraction is equals to mass component divided by total mass. So mass fraction of benzene in waste is mass component. What is that mass component? We have just calculated the mass of benzene in waste is, or in the downstream, is 265. The total mass is 900. Okay, total mass is 900. This W is 900. So the total mass is 900. So mass fraction of benzene in bottom stream comes out to be 0.294. Similarly, we can calculate the mass fraction of toluene in the bottom stream, as we know that this comes out to be 635. Okay, when we are done the toluene metal balance, this comes out to be 635. Okay, 635 kg divided by the total mass, that is 900 kg. Okay, 900 kg, it comes out to be 0.706. 0.706 as the mass fraction of toluene in waste. So here we can say that the material balance calculation as input is equals to output is verified.